I'm delighted to introduce you today our colloquium speaker, Tayar, who's faculty at the University of Florida, which is where she's from originally. But she was an undergrad right here at Caltech, where she worked with Lynn Hillenbrand. Lynn got her interested in stars, I think, and that has persisted, thankfully. She was a graduate student at Ohio State, where she worked with Mark Pinsonow. And I think in true Ohio State fashion, she learned how to work both directly with data, but also with models, really confronting them, and that's one thing in work. She's really straddling that boundary. We tried to lure her back to Pasadena for a postdoc at Carnegie. After that, but she decided to overshoot and go all the way to Hawaii, where she continued to learn about astroseismic data and has used that to do some really remarkable science. We'll hear about it now. Go ahead, please.
Yeah, thank you so much. And thank you all for having me back. It's exciting to be standing at the front of this room instead of hiding in the very back row. So I'm excited to talk to you today about one of my favorite topics, which I've called the evolution of stellar rotation, alone and together, inside and out. And rotation is both an important and a useful properties of stars. Right? When you think about a star is born with a mass, with a composition, and with some sort of rotation rate. And from that point on, it just evolves based on what we think we know about physics. So rotation is one of the very few key properties setting the evolution of a star. It's also one of the biggest uncertainties in stellar physics. Even for low-mass stars, we don't really understand how the rotation, we're only starting now to understand how the rotation is evolving, how that's tied to things like magnetism and convection and all of these other uncertainties in stellar physics and stellar evolution. But we have found that rotation is also a very useful property. In many regions, it's correlated with the age of the star, which would otherwise be particularly challenging to measure for any individual isolated star. And in sometimes we can use the rotation to identify a history of interactions for the star. So telling us if it's interacted with a companion, either a star or a planet, over the course of its life. And in this talk, I'm going to try and convince you that we have empirical data on the evolution of stellar rotation now, from the pre-main sequence all the way to at least the core helium-burning phases. I'm going to try to convince you that binaries are not a negligible portion of this process, right? 10% of stars are interacting with something over the course of their lives, and that there's an awful lot of physics that goes into this. You lose angular momentum through magnetized winds. That loss turns on and off over the course of the star's lifetime. You have internal transport from the interior of the star to its surface, and then, of course, you have the physics of tidal synchronization as these interactions are happening. So in this talk, I'm going to be talking about rotation measured a variety of different ways, and I'm going to use them all interchangeably. So one of the ways you might be familiar with is the velocity broadening of spectral lines in the star. As it's rotating, parts are blue shifted, red shifted, that broadens the lines. The broader the line, the faster the rotation, modulo some inclination angle that you may or may not know for that star. One of the other methods of measuring rotation you might be familiar with is the spots going around the star and changing the brightness of that star. So like on our sun, other stars will also have spots. As they cross the disk of the star will get brighter and fainter and brighter and fainter, with a period that's related to the rotation period of the star. And we've been doing this for a long time. If you have beautiful space-based data, you get a very nice up and down, up and down. You can measure the rotation period of the star. And we've been doing this individually for one star at a time for quite a while now. But people like my postdoc Zach Clater are starting to now apply some sort of machine learning framework to try and do this for much, much larger samples of data, even when they're sparsely measured. And so we can get very large samples of rotation periods this way. The other method of measuring rotation, which you may be less familiar with, is through astroseismology. So if you have one of these beautiful space-based light curves of a star, you see variation over time. That variation is not noise, but is in fact signal. And if you take the Fourier transform of one of these light curves, you get a characteristic shape like this, with frequency on the x-axis here and power on the y-axis. At high frequencies, you see the effects of instrumental noise. At low frequencies, you see the effects of stellar convection. But in the middle, you see this characteristic peak of oscillation modes. And if you zoom in on that peak, it will have some characteristic frequency of maximum power, basically the peak of that Gaussian, which correlates with the surface gravity of the star. And then if you kind of squint at this, it looks like it has regular spacing. Those are spherical harmonics of sequential degrees. You can measure this and give you some sort of large frequency separation, which correlates with the mean density of the star, which is extremely convenient for other reasons, because now you have something that goes as m over r squared and something that goes as m over r cubed, and you have a beautiful mass and a radius for all of these stars. But that's not quite a rotation, right? That I told you that's where we were going. And so you have to zoom in even more to look at the rotation of these stars. So if you take that power spectrum, break it up into chunks, and stack it on top of each other, you get these characteristic ridges of modes of each spherical degree. And so the L equals 0, the radial modes here, look very simple and straight and vertical, nothing complicated going on there. The L equals 2 modes are similar, but over here you have this L equals 1 ridge. And you'll notice that there are peaks that have scattered off of that kind of standard vertical line. If you zoom in on some of those peaks, like this one here, you'll notice they're split into 2 lines. And that splitting is actually a rotational splitting. It's corresponding to, like, you can think of it as kind of like a Doppler shift with and against the rotation of the star. The more splitting, the faster the rotation in the region where that mode is oscillating. And so sometimes that mode is oscillating near the surface of the star, and so it gives you something like a surface rotation period. In other cases, that mode is spending more time in the interior of the star, and so this gives you a better probe of the core rotation rate than of the surface rotation rate. But in either case, you get some measure of rotation, which you can fold in with these other measurements of rotation to put together this generic picture of how rotation is evolving in stars. The other note I wanted to make before we get into the evolution itself is that there is differential rotation in stars. This happens in terms of radial differential rotation, where the core may be spinning faster than the surface of the star. In our sun, we also see something called latitudinal differential rotation, where the equator is spinning faster than the poles of the star. While we've been able to assess radial differential rotation in other stars, we are not very good at measuring latitudinal differential rotation in other stars. Even people who claim that they can measure latitudinal differential rotation aren't able to match this when we do some sort of testing of the models. And so I'm not going to talk about latitudinal differential rotation at all today, only about radial rotation. If I forget to say the radial part, know that it is radial differential rotation. Awesome. Okay, so you start with a cloud of gas. It is collapsing down into cores and into stars. It makes all of these beautiful disks, which we now have all of these beautiful AMA images of, and so forth. At that point, your star is contracting, and so you have this distribution of stars that have disks and stars that don't have disks. When we look in the youngest clusters, we find that the stars that have disks tend to spin a little bit slower than the stars that don't have disks, which suggests, as you might expect, that the disk is somehow regulating the angular momentum of the surface of the star. Another note, because people in this rotation space make their plots in all sorts of different axes, I have tried to mark which side is the fast side on every plot, so that sometimes will be left, sometimes will be right, sometimes will be up, sometimes will be down. And I've put it here, hopefully, to guide your eye. Okay, so the disk is somehow regulating the angular momentum content of the star, but eventually that disk is dissipated, and it seems to dissipate on timescales of a few million years, maybe 10 million years. And while this plot is a little bit older now, the newer plots of distributions of disks and gas mass in young star-forming regions have similar conclusions, where most of the disks are starting to dissipate after only a few million years. And so that leaves behind something like an initial distribution of stellar rotation rates, which ranges from about periods of about 10 days, which again, fast rotators on the bottom here. So that's what stars are born with. And then we take a step in time to the next, one of the next open clusters that have contracted and they've spun up. And so that's a structural change that's affecting the rotation that we measured. And then you can take another step forward in time to another open cluster, and you find that now the stars have started to spin down. Now, they haven't gotten larger again, so that's not a structural change. That's some sort of other physical change that's happening. And what we think is happening is that angular momentum is being lost in a wind in these stars. So there's losing mass. That mass is connected magnetically to the star. It's carrying away an excessive amount of angular momentum for the amount of mass that is being lost, and so it is causing the star to spin down over time. On our own sun, we can actually detect that wind in particles coming off of the surface of the sun. We find that it's a multi-component thing where there's a fast wind and a slow wind. The wind will vary in shape and strength and velocity over the course of the solar cycle. And people are doing all sorts of really interesting physics with that now for the sun. But when we talk about other stars, we don't include much of that at all. We initially started out with an angular momentum loss model that said, young stars are fast, old stars are slow. They spin down as approximately t to the minus 1/2. And we've evolved a little bit more before then, right? That's not quite sophisticated enough for what we want to do these days. Now we're trying to think of it in terms of, okay, it should depend on the rotation rate of the star. It should depend on the Alfvén radius, the magnetic fields, both strength and structure and geometry. It should depend on the rate of mass being lost from the surface of the star, as well as something about the physics of the star itself, something about like the Rossby number, the ratio of the rotation period, and the convective overturn timescale. We don't actually use all of those physical components in detail, but people have tried to use three-dimensional models to kind of translate from the physics you expect to be important into what sorts of scalings can we use to construct an angular momentum loss law that is sufficiently good for our measurements. And so this usually ends up with the loss scaling with like the radius of the star and its mass and its luminosity and maybe the pressure at the photosphere. And so I'm mostly going to be using these more sophisticated models into the modeling that I'm doing, but know that they are still a simplification of the actual physics of magnetism and mass. Okay, so we have these winds are slowing things down. That's good, and we can add that component. But one note that I haven't made yet is the fact that not all stars are born single. And so when you make a diagram like this, now that we have Gaia, you can figure out which stars are non-members that we thought were members and exclude those. But you can also look at stars that are a little bit too bright for their color, probably equal mass binaries or high mass ratio binaries, or low mass ratio binaries, and those tend to pop out a little bit off of the normal distribution, often a little bit faster than we would expect, so they're spinning a little bit faster. And so binarity is probably playing a role in setting the initial angular momentum, setting the lifetimes of the disk, and then perhaps, if there's any tidal interactions, adding additional angular momentum to the system. Okay, so that's all a great physical picture that we're trying to connect to the theory. The nice thing here is you don't actually need the theory at all. In some ways, you can just trace out how the rotation has evolved for stars of any particular effective temperature, which you can convert to a mass, at any particular age that we happen to have an open cluster for. And so Zach made this nice little GIF of you can see each cluster plotted against each other, and the rotation is slowing down over time, empirically. And so when you kind of show all of this at once, for stars like the sun, this picture seems to hold very well. The winds turn on, the stars slow down over time, you could map out exactly how that happened. Great, fine, you can calibrate all of those constants. However, if you look on the right of this plot, you'll notice that's not quite what's happening. They spin down, and then all of a sudden, open clusters of different ages end up on top of each other. And then maybe they start moving again. So they started spinning down, then they stopped spinning down, and they started spinning down again. And that's been a problem for the last couple of years that everybody's been a little bit concerned about. You might ask, is this just a factor of the clusters, right? Maybe there's something funky about the particular clusters you're looking at. Do you see this in the field? The answer is when we take the Kepler distribution of rotation periods, you see them spinning down, and there is this kind of under-density and over-density, where basically they have spun down to a point, then they've stopped, then they've jumped some sort of gap. So it's not just a feature of the cluster data, it's actually happening in the field as well. And you also notice, so this is work from Liler Sao, who's a PhD student at Ohio State, that stars in this particular region where something funky is going on also tend to be more spotted than you would expect for stars of that rotation period and age. And so there is something happening with the magnetism or with the physics of rotation that's happening there. The other question you might have is, well, what happens when we transition from sort of solar stars to lower mass stars? And this is work using this ETF data. You can see the gap as well. And then you notice, if you look right around where the fully convective boundary is, that somehow that gap seems to disappear, or at least become less pronounced. And so one of the leading explanations for what's happening here is this star has a core that is fast spinning as it contracts down, but then sort of gets decoupled from the envelope, at which point the envelope can spin down. The envelope can spin down, but the core is still fast rotating, and so can add angular momentum back. And then at some point, the core and the envelope basically couple together again, so they're spinning at the same rate, and then they evolve as one for the rest of the main sequence. And that, we think, should happen not too far away from this gap is. So we are questioning whether it's likely related to something about the angular momentum transport in the interior affecting the rotation evolution on the surface. And then if that's the correct physical picture, then we should expect a different coupling time between the core and the surface for stars of different masses. So when we're looking at stars on the pre-main sequence, we see strong trends in what's happening with stellar mass. Unfortunately, most of the open clusters are kind of solar-ish in metallicity, so we don't have a great sense of what the metallicity trends are in rotation. But we've noticed that binaries are probably important, and evolution seems to suggest that there is strong radial differential rotation, as well as recoupling between the core and the envelope of the star. I'm now going to pause for 10 seconds before I jump into the main sequence to see if there are any questions before we go on. Yeah?
So this gap, can you go back to the bottom of the gap?
Yeah.
Does that roughly trace the line of constant oscillator?
Yes. It is roughly consistent with that, I believe. And somewhere there are plots of exactly what you expect the Rossby number to be, but how you calculate the Rossby number and where you calculate it will matter, especially if there's differential rotation in the interior. Awesome. Okay. So now that we have a setup from the pre-main sequence, what is happening on the main sequence? I've showed you this plot already where from Kepler, we had 40,000 rotation periods. And now Zach, with his machine learning framework, is able to start pulling similar numbers of rotation periods out of the test data, where we're now looking all sky instead of in one particular field, and so forth. And so when we do this, we can zoom in particular regions that are interesting. And this is work by Ellis Avalon, who is a Hawaii graduate student. And one of the regions you might expect to be interesting is around about 1.2 solar masses. It's what we call the Kraft break. It's where stars transition from having convective envelopes to not very convective envelopes and eventually radiative envelopes. And when you look at a plot of the rotation period in color here as a function of surface gravity and temperature, you'll notice that for lines of different mass, you're very clearly seeing different rotation behavior. You can also try and pull this out and see, well, is there a metallicity trend in the sorts of rotation that we're seeing? In Ellis's sample, we didn't see much of a metallicity trend at all, which actually would be very convenient because we don't know what the metallicity trend starting is supposed to be. And so if there isn't one, that would make everybody's life a lot easier. But of course, you might imagine that we would love a larger sample to be able to test that. One thing we were able to notice is that for stars in close binaries, so things that were spectroscopic, radial velocity variable, we often saw much faster rotation than you would have expected given the distribution. But if you looked at wider binaries, things that could be identified as in Gaia as having a wide companion, we didn't see much of a difference between those and the presumably single stars. And so it looks like wide companions maybe don't affect your rotation, but close companions do, which seems not unreasonable. The next question you might have is what's happening in the interior of these main sequence stars. And unfortunately, we don't have a lot of good core rotation measurements for stars other than the sun. But for the sun, we see the effects of latitudinal differential rotation in the convective envelope. And then once you get into the radiative region in the sun, it looks more or less like everything's rotating at kind of the same frequency. So more or less acting like a solid body. There's been some arguments that maybe the core rotates a little bit faster. People have said that, and people have said the opposite, so it's a little unclear. While we can't measure these sorts of things directly, we can, however, put constraints. Because one thing you might imagine is if you had a close binary system that was tidally interacting, then that binary should synchronize at the average rotation of the region, of the star, right? And so that rotation period of the orbital period and the rotation period, if the whole thing was rotating as a solid body, would all be the same. But if it wasn't rotating as a solid body, if there was spin down in the interior and some sort of rotation profile in the interior, then the surface rotation would not be the same as the orbital period. And so you can actually go out and measure. We have large samples of tidally synchronized binaries. And when you do that, the short orbital periods, the orbital period and the rotation period tend to be about the same. And so it is roughly consistent with the idea that the whole rotation profile is more or less solid body. And so there's minimal differential rotation in these main sequence stars. And so on the main sequence, we see strong mass trends, but subdominant metallicity trends. We see close binaries rotating faster, and the radial rotation profile seems to be approximately solid body. So I'm going to again pause for 10 seconds, see if there are any questions before I go on. Yeah.
The test rotation periods seem to go to rather long periods.
Some of them are probably real, some of them probably aren't. There are certainly detection biases in the sample that you're looking at here. Zach has been looking a little bit at some of the longer rotation periods. They should exist because you should start picking up subgiants right about here. But whether they are all correct or not, I think Zach is a little bit less confident in a lot of the ones up here, but thinks that some of them are real. And so part of what he's been doing is trying to put error bars on these periods that reflect the actual uncertainty in whether we think we detected anything and what it is. Right, so there's usually a spur. You can't quite see it in most of this, but there's usually a little bit of a spur here where the subgiants start getting picked up. You should see some of those in the test data, but I suspect a lot of the stuff over here is probably junk. The stuff in the middle I'm less confident in. You're right, there should definitely be long periods for the M-dwarfs. Whether those are all real or not, though, we're not quite confident yet. Awesome. Okay. So that's where we are on the main sequence. But then the stars continue to evolve. And so as you get to the second half of the main sequence, you can draw these lines of, okay, how should the rotation period evolve with age? We have some relatively simple spin-down model that maybe should be more complicated, but fine, is not terrible. Except that all of a sudden, at kind of the second half of the main sequence, a lot of the stars seem to be spinning a little bit faster than they should be. And that's true. It doesn't really matter exactly what model you're using. If you try and fit it, it's hard to get everything to match at the same time. And so one of the leading explanations for this is that at some particular Rossby number, so some ratio of the rotation to the convective overturn timescale, the braking transitions from the sort of braking we've seen on the early main sequence to something that really doesn't break much anymore. And this was originally suggested using this small sample of astroseismic stars where we had good ages to put on this axis and then good measurements of the rotation period to put on this axis. But you will notice that there are an odd and awful lot of points there. And this is about these are about the rotation periods where our detections become a little bit dodgy, where we stop detecting most of the rotation periods, at least in the Kepler data where they were trying to do these measurements. And so you might question whether this is a detection thing or whether stars actually change how they're spinning down at about the Rossby number, about the age of the sun. One way we've been able to get a little bit more evidence this is actually happening is people have looked at the distribution of rotation periods in age in the field. And so if you assume that everything kept spinning down, you should see a distribution of rotation periods that continues up to these tens of days. And even if you said, okay, well, I can't detect them after some number, that still leaves you with kind of a range up to that number, which should be flat. But if you say they stop spinning down at some particular Rossby number, then they should stack up around that transition. And so you should see more of them right before the detection edge, even if you believe the edge is close to there. And that seems more consistent with what people are seeing in the field. The other thing people have done is the astroseismic measurements of rotation periods don't have the same detection biases as the photometric surface spot periods do. And so you can go out and measure the distribution of stars with these astroseismic surface rotation periods, and you find that they also seem to pile up right at this kind of transition period Rossby turnover. And so something is happening to the spin down at about halfway through the main sequence lifetime. The other thing is these stars continue to evolve after the main sequence. They turn into subgiants, their envelopes expand, their cores contract. And so when they expand into these giant envelopes, they should continue slowing down over time. If you hypothesize that we have this truncated breaking, that the breaking changes at some particular Rossby number, you get predictions as a function of stellar mass that are pretty close to what we're seeing in the data, where there's kind of a mass dependence, but not as strong as you otherwise would have expected. If you don't include the truncated breaking, you expect everything to be rotating more slowly because it's slowed down more on the main sequence. And that looks a little bit less consistent with the subgiant data. So kind of on the whole, we think something is again happening to the magnetic braking around the Rossby number of the sun. And then the nice thing is we have these models of what we think the surface rotation should be doing, but this is a region where we can start to measure the interior rotation. And so with Kepler, people made a bunch of measurements of the core rotation rate, so the rotation rate of the core in the interior of the star, as a function of surface gravity or radius or something like that. And the color coding here is mass, where it seems like kind of stars spin up, then there was a gap in what Kepler had data for, and then it sort of seemed flat. And with TESS, we've particularly targeted stars in this kind of gap here to fill in that, yes, indeed, they do, the cores contract and spin up a little bit, but not as much as you would have expected if they stopped talking to their envelopes entirely. And then at some point, they basically maybe drop a little bit or flatten out, so that they're all kind of rotating at periods of 10 or 20 days on the red giant branch. That is not consistent with pretty much any model people have made about what the cores should be doing. If you said they just spin up and contract, you get something that rotates much faster than what we actually observe. If you include magnetic fields, again, not quite enough, not quite what you want. You could argue that maybe there was some perfect coupling mechanism between the core and the surface. At that point, they should spin down with the surfaces. They're not doing that either. People like Jim have tried to come up with, changing the parameters of these models to tweak them to see if we can get a better fit. You can get a better fit, but so far I haven't seen anything that matches all of the details of the trends and evolution. So we don't entirely know what physical mechanism is doing this transport of angular momentum in the interior of the star, but something clearly is. Okay, so the next thing that happens is as these stars are expanding, they start to interact with more things that are near them, because suddenly they're the size of the orbit of a planet or another star. And so here at Caltech, you've probably heard some of the catastrophic interactions, things like luminous red novae or big transition stars that are trading mass back and forth. You may have heard of the sorts of interactions that really change the structure of the interior, really merge the two stars together and totally change their structure. But even before that, there are going to be some stars that interact and don't totally change their structure, but do change their rotation. And so, like I was saying, we have some sense of what the rotation in the interior of the star should be. The core should be rotating fast, the surface should be rotating slow, And where exactly this transition happens, we don't know. Exactly what the shape of that is, we don't know. But in any case, we know the core is fast and the surface is slow. And then you can go out into the data, and sometimes you find a weird object like this one, where the core is rotating fast, like it's supposed to. The surface is rotating slowly, like it's supposed to. And then the actual surface of the star, not the envelope, but the surface itself, is rotating fast. And so this green point here is coming from the astroseismology of the interior. It gives you some probe of the envelope rotation rate, some average probe, whereas the V sin I here in pink is giving you the actual surface where the spectral lines are being formed. And so the only reasonable explanation I have been able to come up with yet for a profile like this is that somehow you have dumped fast rotation onto the surface. So either through tidal interactions with a very close companion or by actually consuming something with mass, not a large amount of mass, but a small amount of mass. So we're thinking hot Jupiter, M dwarfy type thing. You have spun up the very surface of the star, and it has not yet had time to equalize the entire convective envelope. And so we think these interactions happen where you affect the rotation before you affect the structure. This is also something you can study in populations of stars, even when you don't have, beautiful data of the interior rotation over both the core and the envelope. You can look at the rotation velocity of stars on the red giant branch as a function of, say, their radial velocity variation, which is going to tell you something about the location and size and mass contrast with the companion. And if you have a closer companion that's larger, you're going to spin up more. And so you can draw these kinds of lines of what you would expect for the rotation to do as a function of the interaction with some companion. And you can go out and measure the distribution of rotation periods as a function of the radial velocity variability of those stars, and you see something that roughly matches what your expectations are. So there are indeed a lot of stars tidally interacting with something that's spinning them up on the red giant branch. And so you can pick out these stars using spectroscopy. You can pick them out even sometimes using Gaia. And so this is work from Rachel Patton, where she's identified a large population of these, which are sometimes come out a little bit cooler than you would have expected, are definitely rapidly rotating, and almost certainly interacted with something. And so we think about at least 10% of stars are undergoing some process like this over the course of their evolution up the red giant branch. Okay, so for subgiants and red giants, we're seeing mass-dependent surface rotation rates. We're seeing mass-independent core rotation rates. We're seeing minimal metallicity trends, except maybe we know there are more close binaries at low metallicity, so that might affect the distribution of rotation periods. And then we're seeing significant radial differential rotation in these stars. And we know that binaries can spin up the surfaces in particular. Okay, I'm going to again pause for 10 seconds. Go.
Yeah, that was really cool, the result of the differentiation between the surface and the core. But is that a very, what's the characteristic time if you hit like an envelope runs into it? How long are you looking at privileged moments?
Yeah, great question. Haven't seen a great model of what's supposed to happen. So you're definitely talking about like a dynamical tide interacting at some particular radius at some time first, and then presumably I would have thought it would very effectively homogenize over the convective envelope. So either we don't know what we're talking about and something about our data is leading us astray, or we have caught a very particular moment for this particular star. We have a reasonably large sample, but not a great sample, so it's a little bit odd that we would have caught one in kind of a short time scale I would have thought the convective envelope would have homogenized over, but sometimes you find rare things. Or something I don't understand about how angular momentum is transported from the surface to the interior. So yeah, great question. Don't know. Would love to find a real sample that will tell us the answer to that. Yeah? Because this is a lower red giant. So our radius here is 8 or 10 arson, I think. And so if you say V sin I of a few at the solar radius, you've expanded a factor of 10 squared.
This is expected, and then you're measuring something that's a few 10.
Exactly. So this difference to this difference, maybe we haven't quite got the angular momentum content of the model right. could be a little bit of an upper limit depending on exactly how you do the analysis. You can make the envelope rotation a little bit slower. So it could be that this is not so far from this, but this and this are very far apart, and this is nothing like what I would have expected or what I've seen in kind of any other star of this type. Right? It's very rare for me to have a core rotation period, a star of this radius, and then detect a V sin I at all.
So this one is showing the special case, not the general case.
Exactly. Yeah. The general case is the more disappointing looking this, where I have a lot of core rotation periods on the right half of this plot and almost no surface rotation periods. And so I'm having to try and use models to translate between what I think the surface must be doing and what the core is actually doing, because periods this long and velocities this slow are very hard to measure. Great. Okay. So stars continue up to the tip of the red giant branch, and then eventually they're able to ignite their helium and contract back down to the core helium-burning phase, or the red clump in these metal-rich populations. You can look at the distribution of surface gravity and stellar mass. You can use models to predict where the stars should be rapidly rotating. That would be when they're massive and small, versus where they should be slowly rotating. That would be where they're large or low mass. And then you can look at where you actually measure rotation. And you'll notice this kind of arc here at a particular gravity that corresponds to the gravity of the core helium-burning stars. So quite a lot of the detect rotation are in the core helium-burning phase. That's interesting because these are things that have gotten big, have contracted back down, and suddenly they're now spinning faster than they were when they were the same size before. And so these are a lot of the stars that we think have interacted with something over here. But then you can also look on the left half of this plot where the stars are supposed to be rotating rapidly, and they are not. In rotation velocity, we don't really see them at all. In spots, we sometimes see them, but they're rotating faster than we would have expected, or they're rotating much slower than we would have expected them to. And so there's something, again, where our original explanation of the physics isn't quite right. And so if you take the distribution of rotation velocities in this core helium-burning phase for the more massive stars, so say 2 to 3 solar masses, you get a distribution that peaks around 3 kilometers per second, maybe extends out to 5 kilometers per second. If you do a simple calculation of how you expect the angular momentum loss to happen in these sort of magnetized winds that we've parameterized, you would have predicted a distribution out to 10 or 20 kilometers per second, which would have been easier to measure than the 3 kilometers per second people are actually seeing. And so when you use these more sophisticated angular momentum loss laws that I was talking about before, you get something that actually does predict more loss in this regime because of the dependence on luminosity and radius. And so you predict a distribution that is more consistent with what we actually observe. And so it's no longer sufficient to use these simplified wind laws. You have to use these more sophisticated values. You can also look at the evolution of the cores of these stars. And you'll notice as the stars evolve from left to right on this plot, in the core helium-burning phase, the core rotation periods are slowing down. Now, the moment of inertia of the core itself is not changing very much in this phase. So you would have normally expected it to be kind of flat. But instead, it is very clearly slowing down as the envelope of the star expands. And so that's telling you that there must be angular momentum transport between the cores of these stars and their envelopes. You don't even need a model to tell you that. But if you do have a model, you can predict what the distribution of surface rotation rates should be for these types of stars. And you find that they are indeed spinning down, but they're maybe a little bit slower than the cores that we're measuring. And you can look at whether this is some function of stellar mass. Doesn't really look like it to me. Whether this is some function of metallicity. Doesn't really look like it to me. And so you end up with a core-to-surface contrast that's sort of a factor of 2, and is the sort of thing you could imagine containing even in the convective envelope itself. I can't say for sure whether this differential rotation is located in the core of the star or whether it is located in the convective envelope, but it's a small enough ratio that you could just kind of hide it in the convection zone. Okay, so in the core helium burning phase, we see surface rotation that is somewhat mass dependent. We see core rotation that has minimal mass dependence, which doesn't make any sense, but fine. There's minimal metallicity dependence, except maybe the number of binaries. And there is less differential rotation between the core and the envelope than we saw in the first ascent giant branch. So the core and the envelope must have started talking again. So they started out decoupled, they recoupled on the main sequence, they decoupled on the giant branch, they recoupled during core helium burning, and then perhaps they decouple again during the AGB phase. And so it seems like core burning cores are coupled, and don't really know what the physics of that means, but it probably tells us something about the mechanisms that's transporting angular momentum in the interior. And then we know that binaries will spin up the surfaces of some fraction of these stars. Okay, cool. So hopefully I've convinced you that we have empirical data on the evolution of stellar rotation, both the interiors and the surfaces, and that binaries are not a negligible part of this process. There's a lot of physics that goes into this. You have to talk about angular momentum loss. That loss turns on and off and on and off over the course of the star's lifetime, or at least gets stronger and weaker and stronger and weaker. There is internal angular momentum transport happening between the interiors of these stars and their surfaces, and tides are going to be a strong factor here. And since I have another minute or so, I don't always show these plots, but you might be asking what happens next, right? After the core helium burning phase, we have the asymptotic giant branch, and then stars turn into white dwarfs. We don't have great constraints on exactly all the physics that happens during that time. It's much more complicated to model. But one thing we do notice is that the kind of angular momentum content of those cores in the core helium burning phase is roughly consistent with the angular momentum content of the white dwarfs they produce. And so you don't necessarily need to have anything happen to them, any angular momentum transport, after about the end of the core helium burning phase. You could spin them up and slow them down or something again, but you don't necessarily need to. The other thing people have been looking for is a mass dependence, because if this angular momentum transport is happening, it should happen on some time scale because of some physical process. And as you increase the masses of those stars, the time scales get shorter. For white dwarfs coming from progenitors of like 3 solar masses or below, which is most of what I've shown so far, there's almost no mass dependence in what you see in the white dwarf rotation periods. But you may start to see something around 4 solar masses, which, if it becomes a generic feature and not just a handful of points, might tell you something about the time scales of angular momentum transport in these stars, which hopefully will allow us to have another constraint on what the physics could be. So with that, I'll stop talking and see if there are any more questions. Right. In vague terms, it's not unreasonable, right? You've got mass flowing off on some sort of shell launched at some particular radius. That mass is carrying away m over r squared, depending on the launching radius. And so the mass that is left behind has less angular momentum. However, what actually happens is that mass gets coupled to the magnetic field lines out to some radius that is much larger than the radius of the star. And so there becomes a launching point at a much larger r. And so the m over r, the mr squared, the r is much larger than you would have thought. And so that mass carries more than the delta mass amount of angular momentum away, which slows the star down significantly as opposed to not very much.
When you start looking at Gaia giving us more information about binaries,
Yeah.
there's already this term, the Louis term, that lets you get an idea that there's potentially a binary. Try to correlate directly with some of the Gaia binary.
Yeah, so some of that is in Rachel Patton's work, and some of it is left to be done, I think, where she's indeed looked to try and get a sense of what's marked as a Gaia binary and how that relates to the rotation. We've seen it a little bit as well in clusters where you can say, this is definitely a binary and it's offset from the rotation. I think we are very close to being. Here are a set of stars that are in wide binaries. Here are a set of stars in close binaries. Here's a set of stars that have interacted very recently or are interacting now. And here's a set of post-interaction stars. And being able to draw the line between those populations is, I think, something that's going to happen really interestingly in the next couple of years. And so I'm really looking forward to seeing some of that.
I'm really interested in the evolution of stellar rotation in the most massive stars. And I know she didn't really discuss them in too much detail, but I was just wondering, in particular with, like, say, an O-type star with 20 solar masses, what is the general conception? How would you expect that to evolve, say, to a Wolf-Rayet type phase? You know, you expect them to all break because they're losing so much angular momentum, but I guess binary math can seem what's close to.
Right. So the reason I didn't talk about those stars is because there's much harder, and as far as I can tell, the data constraints are not as good yet. So there definitely should be a wind around those stars. There is a strong wind around those stars, but you don't have the same convective zone driving a dynamo, driving a magnetic component of that wind, and so that wind, in theory, should carry away less angular momentum. They certainly spin faster than the low-mass stars, and there's maybe a little bit of a change over their lifetime, but not quite as much. But then they also have these catastrophic binary interactions, which can either spin them up or slow them down, depending on exactly how that progresses. And then you've lost a lot of mass, so you can strip off the top layers, and what you're left with behind is telling you about the rotation of that more interior region and its history. And so connecting those dots has to be done very carefully, and it requires knowing where a star is and where it came from, which is much harder for those higher mass stars. So I think there should be some slower spin down over time, and then cores that seem to rotate faster and maybe don't have as much time to transport angular momentum between the core and the surface. But seeing that in reality, there hasn't been as much data yet. Yeah.
So for short period binaries that undergo tidal interaction, so can there also be like mass transfer, and can that change the rotation of those stars?
Absolutely. And exactly how that mass transfer happens is going to matter, right? Because if you put it in at the pole, then that's very different than driving it in at the equator. You've changed the tidal forces, you've changed the chemistry, you've changed the gradients, whether you've driven extra mixing or not driven any mixing at all and prevented mixing are all kind of scenarios that can happen. And so I think it's probably going to be the data that leads in that field of trying to figure out exactly how the interactions between stars happen and what they actually mean, because you have to kind of keep account of how the mass is transferred, where it's transferred, when it's transferred, from where to where, right? You might imagine that in a tidal system where one star is the orbit is backwards from the rotation of the star, you're dumping angular momentum going the other way. And so you can actually totally change your distribution of angular momentum. And so people have done cool simulations of young stars where they're accreting angular momentum from various different vectors, and like you can watch the angular momentum vector change over time as different events get dumped in. Don't know exactly whether that plays out in reality, don't know how it will happen in kind of two stars, one dumping matter onto the other, but it seems like there's a lot more complexity that could happen there, and it will be interesting to see whether it does. You can get some constraints. Let's see, if you have rotation period and you have, so that gives you a radius and you have something like a rotation, it will tell you some minimum amount, potentially, especially on the giant branch, some minimum amount of angular momentum you must have gained. But whether you gained that a long time ago and gained more of it and then spun down versus you gained it very recently but only exactly that amount, there are trade-offs there. So it's an upper limit perhaps, or a limit perhaps, not exactly I haven't yet seen a way to trace out exactly the history of the star. People have tried to do some really interesting stuff in like open clusters, like M67, where you have kind of the remnant white dwarf and you have the star itself, and it's not where you would have expected, but you know what composition it started out as and you know what age it is, and so you can kind of come up with a track that allows you to get to where it is now with some reasonable mass transfer parameters. And so there are a handful of those, but you need an awful lot of constraints to do anything particularly valuable.
question, Jamie. Can you go back to the plot I asked you about the constant Rossby number?
Constant Rossby number. Oh, yeah.
All the measurements of rotation periods.
Yeah.
Yeah, sorry,
Yeah, back a lot of slides. Something like that.
So my understanding is the cutoff at the upper edge
Mm-hmm.
of these plots is also roughly constant Rossby number, and so that's been argued as
Yeah.
the dynamo turns off at some particular Rossby number.
Mm-hmm.
So why not explain this bottom gap as the dynamo has some kind of change at that Rossby number?
So that is one way of explaining it. It's a possibility. You have to figure out how to turn it off and then turn it back on to get to where it was. It's not impossible. You could come up with some scenario. And people have tried to argue there's some particular Rossby number where you change from like spots dominated to faculae dominated, so you have fewer detections of spots in that regime, and so you have a gap that doesn't actually change anything about the rotation evolution. It seems pretty clear at this point that the rotation evolution is changing because the clusters are tracing one particular age and kind of cross this gap. But it is possible you could have some change in the dynamo that changes again and then changes again. It's not impossible.
If this was due to core envelope decoupling and then recoupling, it seems like it would be quite a coincidence for that to happen at a constant Rossby number.
Yep.
So,
Yeah.
possible, but
Yeah, exactly. That's when you go to meetings who are specifically about this gap, you'll hear several different explanations. I think we've killed most of the population-specific ones, but most of the physical ones are still plausible.
okay, any last questions? All right, let's thank Jamie again.